The James Webb Space Telescope is constantly pushing out how far we can see in the universe, detecting ever fainter and fainter galaxies. The current most distant galaxy that we know of is thanks to JWST, and it's Jade's GSZ 14-0, the light from which took 13.4 billion years to get to us. But the universe has expanded since then, meaning that galaxy will be much further away today. If we correct for expansion, Jade's GSZ 14-0 would now be just under 34 billion light years away. But we've not known about this galaxy for very long at all. It's a relatively new discovery. It was announced in this paper by Carniani and collaborators in May 2024. And that announcement got me thinking about the galaxies that have held that title of most distant galaxy known over the years. Because if you've been following me for a while, you might remember this video from last year where I said this.
So for example, JWST just confirmed the distance to the most distant galaxy known, GSZ 13.
Or you can go back even further in my videos to January 2021 where I said this.
But for now, let's talk about the fact that we now have a new most distant galaxy ever found in GN-Z 11.
And then while I was thinking this, the weird ways that the universe works, I was at a conference last week, the European Astronomical Society meeting in Padova in Italy, where Professor Richard Ellis from UCL gave a plenary talk about studies of early galaxies with JWST. And he showed this plot showing the distances of the most distant galaxy known and how that changed year on year. And that was it. I just knew at that point I had to make this video on the record holders of the most distant galaxy known. But before we dive into that list of record holders, I know many of you out there are budding astrophysicists, but many of you tell me that a barrier to that dream is your confidence in your math skills. And if that's the case for you, then you are gonna love the sponsor of today's video, Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in science, maths, data analysis, programming, and AI. It's a learning platform designed to be uniquely effective, right? They have this first principles approach to each new topic, which helps you build understanding from the ground up. And this hands-on problem-solving learning technique has been shown to be 6 times more effective than just passively watching lecture videos. Now, finding the most distant galaxies in the universe is like trying to hunt for a needle in a haystack of astronomical data. So if you're interested in this, you're gonna need data skills. Thankfully, Brilliant recently launched a ton of new data analysis lessons, all of which uses real-world data to train you to see trends and make better informed decisions. So whether your goal is to become an astrophysicist or to help you along another career path, you can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/Dr. Becky, or you can click on that link in the video description below. With that link, you'll also get 20% off an annual premium subscription. So thanks again to Brilliant for sponsoring this video and continuing to support this channel. And now let's think about the very first most distant galaxy known. Because you could argue that it's our own galaxy, right? Our own island of stars in the universe, the Milky Way, that was the first galaxy known. But I'd argue that humanity didn't really understand what the Milky Way was until we figured out that it wasn't the entire universe and that there were other galaxies, other islands of stars out there. For that, we have to go back to the 1920s and Edwin Hubble. Now, back in the 20s, everything that was a bit fuzzy and didn't look like a star were all lumped together and called nebula. And one of those was the so-called Andromeda Nebula. And in Andromeda, Hubble noticed a type of pulsing star that was variable, that was known to be brighter the longer the time between pulses. All Hubble had to do was to measure how bright the star appeared and then work out what was the time between the pulses. That then gave you how bright the star should be, and from comparing the two, you could work out how far away the star was. In the same way that you know roughly how bright car headlights are, so from how bright they appear at nighttime, you know how far away a car is. When Hubble did that back in 1925, he worked out a distance to this star in this Andromeda Nebula that was far larger than the known size of the Milky Way, which came from, the most distant star known at the time. That discovery settled a long debate about the size of the universe, which I've made a video about before if you want to check that out. So technically, I'd argue that Andromeda was technically the first most distant galaxy known. But Then, in 1929, Hubble pointed out that the distance to galaxies was also correlated with what's known as their redshift. Now, redshift is just a Doppler shift. It's the same thing that happens when a siren races past you and you hear it going from higher pitch to lower pitch as the waves get squashed and stretched out. Similarly, people noticed that light was being stretched to longer and longer wavelengths, so making it appear like galaxies were moving away from us at speed. And again, it was much later that people would settle on an explanation for redshift as the expansion of the universe in the form of the Big Bang Theory. There were many other explanations raised, and again, I've covered all of that in another of my great debate series if you want to check that out. But throughout the 20th century, people have been measuring these redshifts of nebula or galaxies without really understanding what it meant. And that work was especially pioneered by Vesto Melvin Silfer. And so once that significance of the correlation between redshift and distance was made in 1929, that meant we had a new record holder for the most distant galaxy known. NGC 7619, an elliptical galaxy in the constellation of Pegasus that had a recessional velocity of 3,779 kilometers a second, i.e. a redshift of 0.012, with the light taking 171.7 million years to get to us. But NGC 7619 did not hold that title for long, as astronomers in the early 20th century almost became obsessive at searching for more distant galaxies, just by looking for sort of like faint, fuzzy smudges on photographic plates, so images that were taken by telescopes at the time, and then following up on those faint, fuzzy smudges by taking a spectrum with another telescope. This is where you split the light through a prism to get how much light at each color or wavelength you have. That way you can see any features in the light of the galaxy, like missing colors where molecules in stars' atmospheres have absorbed light, or extra bright colors where gas around newly formed stars is glowing at those wavelengths. It's those features that allow us to track how much the light has been redshifted by, and therefore how fast the galaxy appears to be moving away from you at. And if you know the expansion rate of the universe, you can then work out, okay, well then how long has the light from that galaxy been traveling for, and you can sort of work out a rough distance. Now, as we just heard, back in the early 20th century, there wasn't really a consensus on whether the universe was even expanding, never mind how fast it was expanding at. So in that time period, people tended to just quote the velocities that the galaxy appeared to be moving away from us at, knowing that it was correlated to distance, but still unsure like sort of what that conversion actually was. Now, it was Milton Humason, who worked very closely with Edwin Hubble at Mount Wilson Observatory in California, who really led this campaign in the 1930s to find ever more distant galaxies, smashing his own records multiple times. First in 1929 with elliptical galaxy NGC 4860, which has a velocity away from us of 7,800 kilometers a second. Then in 1930 with the brightest galaxy in the Ursa Major cluster, which has a velocity away from us of 11,500 kilometers a second. Then again in 1931 with the brightest galaxy in the Leo cluster, which has a velocity away from us of 19,300 kilometers a second. Then again, in 1936, with a more comprehensive list of many galaxies' velocities, thanks to a new instrument on the 100-inch telescope at the observatory, here you can see that he finds the brightest galaxy in the Böotes Cluster has a velocity of 39,000 kilometers a second away from us, and that the brightest galaxy in the Ursa Major 2 cluster has a velocity of 42,000 kilometers a second away from us. That measurement turned out to be incorrect. It's more like 37,000 kilometers a second recessional velocities. So we're going to give the crown here to the Böotes brightest cluster galaxy with a redshift of 0.132. Then after 1936, the rush to find ever more distant galaxies took a bit of a backseat. World War II broke out and physicists found that they were needed in the war effort. Then after the war, they had a little bit of a catching up to do, especially in terms of building new telescopes. But by the end of the 1940s, the newly installed 200-inch Hale telescope at the Palomar Observatory was up and running. And that meant that Humason could rekindle his search for the galaxies with the highest recessional velocities, finding a faint galaxy in the Hydra cluster in 1951 that had a velocity of 61,000 kilometers a second away from us, which is a redshift of 0.23. It was a value that wasn't officially published though until 1956. But then Humason's record was smashed this time by Rudolf Minkowski, who in 1960 published a paper reporting on the spectrum he'd obtained with the 200-inch Hale telescope for the object 3C295, which had been first found using radio light telescopes. It was incredibly bright in radio light, but there was nothing in that part of the sky, like a star for example, or a known galaxy already, that it could be associated with. So the assumption was it must be a faint, distant galaxy. And it was Minkowski that managed to get the spectrum and found its redshift was a factor of 0.4614. Note how he doesn't quote the recessional velocity at all at this point in 1960. He switched to just quoting the redshift factor. And if I had to make a guess at why, it's probably because this is where the equation that you use for redshift switches as you get to higher, what we call relativistic velocities. When the velocity is low, you can just simply use v over the speed of light, whereas when the velocity is high, you have to use this special relativistic formula for redshift. And that is a trend that seems to have continued with Martin Schmidt's work, again following up on objects first found with radio light telescopes. But this time for quasars, quasi-stellar objects. Things that sort of look like stars because they are so bright, especially in radio images where they were first found, but also in visible light images as well. Sometimes you can't even see the galaxy in the background, but when you take a spectrum to get at the redshift, you find they are at huge distances. What you're actually seeing is the light from the gas spiraling around a supermassive black hole, and it was only once the Hubble Space Telescope launched in the 90s that we were able to make out the faint galaxies around them. So in 1964, Schmidt reported the redshift of the quasar 3C147 as 0.545. But just a year later, he absolutely smashed that record when in 1965 he reported that the quasar 3C9 had a redshift of 2.012. Not only did he smash the redshift 1 mark, but also the redshift 2 mark. And it's not just a big jump in redshifts, it's a big jump in distances as well. 0.545 is a look-back distance of 5.5 billion light years, whereas a redshift of 2.012 is a look-back distance of 10.5 billion light years. That was right on the edge of the lower limit of the estimated age of the universe at the time as well, so it was big news. Time magazine even picked up the story. Then through the rest of the 60s and 70s, progress slowed a little bit on this. There were just sort of slow, ever incremental jumps in redshift as more and more distant quasars were found. But then in 1973, Carswell and Strittmatter published the first quasar with a redshift over a factor of 3, which is named OH47. And then through the 70s and 80s, those slow incremental jumps continued with ever more distant quasars found until 1987, when the first quasar over a redshift of 4 was reported by Warren and collaborators. And at the end of the 80s, there was a flurry of a few more quasars found with redshifts over 4 until 1991, when Schneider, Schmidt, and Gunn announced the discovery of the quasar PC1247+3406 at a redshift of 4.897. And they did this using a slightly different method, this time with something known as Lyman alpha absorption. And this is due to hydrogen clouds between the galaxy and us here on Earth that absorb light at a very specific wavelength. And as the universe expands, that wavelength gets redshifted, but yet more light gets absorbed, leading to a huge drop-off at the wavelength where the first absorption occurs. And it's that allows you to pinpoint the redshift in a spectra. But it also gives you a way of picking out very distant galaxies in just images as well. Images that are taken through filters that only let in certain ranges of wavelengths at like blue light, green light, and red light. Because of Lyman alpha absorption, you can only see the most distant galaxies in the reddest filters, or the reddest color images. Now the quasar PC1247+3406 held the record until 1997, when finally, for the first time since the 60s, something other than a quasar became the most distant galaxy known. Frank and collaborators had used the recently launched Hubble Space Telescope to observe the cluster CL1358+62, which is a fairly nearby galaxy cluster at a redshift factor of about 0.33. But in that image, they noticed a very faint red arc, which they suspected to be a background galaxy that's had its light bent by the nearby cluster, which acts as a lens to magnify the much fainter galaxy in the background. After spotting it, they excitedly applied for time on the Keck telescopes in Mauna Kea in Hawaii to get a spectrum of this thing and found the redshift to be 4.92. Again, the first time that just a galaxy without an incredibly bright growing supermassive black hole, i.e. a quasar, had been the most distant thing known since 1964. It did not hold on to that record for very long though, because just 9 months later in 1998, that threshold of redshift 5 was broken by Day and collaborators, who had found a galaxy dubbed RD1 with a redshift of 5.34, again using that Lyman break drop-off method. But RD1 sadly only held the title of the most distant galaxy known for a single month, before Wayman and collaborators published their highest redshift galaxy from the iconic Hubble Deep Field image. They first found the reddest galaxies in that very famous image, and then again observed those with the Keck telescopes and found that the galaxy HD 4-473.0 had a redshift of 5.6, meaning the light took 12.7 billion years to get to us. And with that discovery, humanity was seeing back to the first billion years of the universe's lifetime for the very first time. Now, HDF 4-473.0 held onto the title for about a year before Hugh, McMahon and Cowie in 1999 found a similar looking galaxy at a redshift of 5.74 known as SSA22-HCM1. But then, with the turn of the millennium, the quasars had one last hurrah. The Sloan Digital Sky Survey had begun to collect data in 2000, taking images of the sky which are about 8 times the size of the full moon at one single time. And in just the commissioning data from the Sloan Digital Sky Survey, Fan and collaborators in 2000 spotted a quasar that again was seen in red colours but not blue, and when they followed it up using the Keck telescopes had a redshift of 5.8. And then in 2001, Fan and collaborators found yet another quasar in SDSS data this way with a redshift of 6.28, breaking that redshift 6 threshold just 3 years after the redshift 5 threshold had been broken. That only held the title for 4 months though, before Hugh et al. In 2002 reported another lensed galaxy, this time in the Subaru Deep Field, known as HCM6A. Again, they followed it up with the Keck telescopes and found a redshift of 6.56, dethroning the quasars once again, and the BBC picked up on this result back when their website looked like this. What a blast from the past. However, yet more distant galaxies would be found in this Subaru Deep Field, which was taken by the Subaru telescope on Mauna Kea with an exposure time of over 30 nights in total. That was all summed together, all with the goal of detecting the faintest galaxies at the greatest of distances. The first was reported by Kodaya and collaborators in 2003 at a redshift of 6.578, and the second in 2005 by Taniguchi and collaborators at a redshift of 6.597, and then finally by Ai and collaborators in 2006 with a galaxy known as IOK-1 with a redshift of 6.96. Now, IOK-1 held onto the title for about 3 years or so until the end of the decade, when in 2009 we had something completely different.
And now for something completely different.
In April 2009, a gamma ray burst was detected by NASA's SWIFT telescope. These are some of the most energetic explosions in the entire universe, and they're thought to occur when a massive star goes supernova and dies, but we still don't completely understand them. And when one does go off and is detected, we immediately follow them up with other telescopes from across radio, visible and infrared light to try and learn more about them. Which is exactly what Tanvir and collaborators did using the VLT, the Very Large Telescope in Chile, to get an infrared spectrum where they found a Lyman alpha drop-off in the light of the galaxy hosting this gamma ray burst, putting its redshift at 8.2. 2022, smashing both the redshift 7 and redshift 8 thresholds all in one fell swoop, which meant that it held on to that title of most distant galaxy known for a good 6 years while those Lyman alpha dropout searches in visible images caught up. But eventually they did, and in 2015 Robert Spessani and collaborators reported 4 galaxies that only appeared in the reddest images in the candle survey done with the Hubble Space Telescope. Zitrin and collaborators then followed up these galaxies, again using the Keck telescopes, and reported a redshift of 8.683 for the galaxy they dubbed EGSY 8P7. But it was at this point that we were really starting to reach the limits of what was possible using the Hubble Space Telescope. Because it can only detect light out to a certain wavelength, so as the light from distant galaxies gets redshifted, it's no longer possible to see that Lyman break anymore. Plus, galaxies get fainter and fainter with increasing distance, which means it gets even more difficult to actually get a spectra of the galaxy once it's found, because the telescopes that we had at the time, like the Keck telescopes that we do still have, they can't detect enough light from that galaxy with the limited collecting power that they have to get a spectra that's like clean enough to be able to pinpoint where that Lyman alpha break drop off occurs. So this is where things start to get a little controversial, because in 2016, Ush and collaborators claimed to have found a redshift 11.09 galaxy using the Hubble Space Telescope, a galaxy that would get dubbed GNZ11. Now their evidence was based on the fact that in the images, the light drops out in the bluer filters, and they got a very noisy spectrum that they took with the Hubble Space Telescope, which they claimed a model with a Lyman alpha dropout at a redshift of 11.09 fit their data better than any other model of like a lower redshift galaxy. And so from 2016, GNZ11 became sort of like the candidate most distant galaxy known, where we were really pushing the Hubble Space Telescope to its limits. But in early 2021, Jiang and collaborators actually managed to detect emission from carbon, again using the Keck telescopes, that allowed them to put a redshift of 10.957 on GNZ11, just below that redshift 11 threshold. But then later in the year, in December 2021, we had the launch of the James Webb Space Telescope. That meant we had a bigger telescope that could see fainter things and was sensitive to light out into the infrared, where the Lyman drop-off for more distant galaxies was occurring. And in the first few months of JWST's operation, the focus really was on GNZ11. There were a lot of proposals put in to observe it in the first year of JWST's operations, all with the hope of trying to confirm if it really was at such a high redshift. And eventually, Bunker and collaborators in September 2023 did exactly that, finding a slightly lower redshift of 10.603 with a beautifully detailed spectrum from near-spec onboard JWST. Problem is, by the time they published that spectra with that redshift in September 2023, JWST had already absolutely smashed that redshift record. Sure, there were claims of redshift 20 galaxies in the very first images of SMACS 0723, but these again were just based on images alone. They weren't spectroscopically confirmed. Similarly, Robertson and collaborators from the JADES team identified 4 promising high redshift galaxies using that image dropout method in 2022, but by February 2023, Curtis Lake and collaborators had published the spectra of those 4 galaxies, which were obtained using JWST. So they're absolutely gorgeous in terms of the detail you get. And they found that JADE's GS-Z13 had a redshift between 13.17 and 13.2, depending on where exactly you assume the drop-off is happening in the spectrum. This was the very first time that we had any spectroscopically confirmed redshifts with JWST, never mind the most distant galaxy ever confirmed with JWST as well. So it was a huge deal, especially because it came out 7 months before the highly anticipated GNZ11 redshift was confirmed. It meant that we were able to see back to when the universe was just 300 million years old, an extra 100 million years further back than with GNZ11. And that meant that according to our best models of the universe, we now had a hope of being able to pinpoint when the first stars in galaxies in the universe formed. Now, as we know, Jade's GSZ13 held on to its title for just over a year before, in May 2024, Carniani and collaborators announced they'd found 2 new highest redshift galaxies, one at a redshift of 13.9 and one at a redshift of 14.32, absolutely smashing that redshift threshold of 14. That galaxy is known as Jade's GSZ14-0, although note that this work technically hasn't gone through peer review yet. It is data that is quite literally fresh off the telescope. And who knows how long Jade's GSZ14-1 will hold on to that title of most distant galaxy. It could be that there's another one found before that paper even makes it through peer review. Hell, it could be another one found before I even finish the edit for this video. Who knows? Because we really are in an era of complete transformation when it comes to galaxy studies. We are learning so much thanks to both the James Webb Space Telescope and the Euclid Space Telescope, and I, for one, cannot wait to see what they find next. I'm thinking about making this like a series, by the way, like record breakers, you know, like the closest exoplanet known to Earth or the most massive black hole known. So if you like that idea, let me know down in the comments and let me know if you have any other ideas for, you know, record breakers, what it could be. Probably should shut that window. Motorbikes. It's somehow both absolutely chucking it down outside and is boiling hot in here. And the two do not compute in my head. Where is my tissues? I have a runny nose. There are no tissues. 1247 plus 3406. 1247 plus 3406. 1247 plus 3406. Need to give quasars better names than just coordinates. We sent by someone who used Keck. Did you smash my redshift record right in the head? That doesn't make any sense. Oh, shush.